welcome to my presentation. My name is Julia Reisinger. I'm from TU Wien, Technical University of Vienna, and I'm presenting to you Scan2Beams, moving towards an automated modeling and analysis of structural industrial building stock. The whole research is conducted within our funded research project Restock Industry, and the whole research project with a lot of industry partners has the goal to create a digital framework for circular economy-oriented reuse of existing building structures for vertical production in future. A little bit about the background and the problem statement. So we have a lot of land consumption, not just in Austria, but worldwide, and how can we look to decrease our new land consumption and use our existing properties and buildings we have. And especially in production, it's about getting more productive, but getting productive vertically and not expanding horizontally. And for example, there are some numbers in Austria. So we have more than 1,100 new industrial building permits per year, but we have 82,000 existing industrial buildings, whereby more than 6,000 are unused, and we are looking how can we reactivate them and then also convert them to adapt them with multi-story buildings, because usually they're just one story, right? And what is very relevant for allowing vertical production in future, it's the structure of the system, the structural analysis. So usually they're just built for their current use with one floor, but if we adapt them, we really need to look at the structure. So this is a little bit the background why we're doing what we're doing. The related literature and state of the art. So there is a lot of Scan2BIM, but we were thinking, okay, how can we go through the building, scan the building, and get directly the finite element model out of it without creating a BIM model, because we wanted to know more information about the structural capacity. So there are some related literatures. They are doing Cloud-to-FEM, but mostly on heritage structures, meaning a lot of masonry structures and tunneling structures. So, and these existing approaches are usually modeling full scenes and often including non-structural elements, having walls, but however, industrial building structures, they have these skeleton structures. And also when you go into an industrial environment, you have a lot of noise in the point clouds with pipes, with production machines, like there's a lot of things going on, and so we need to filter out. And this is what we're doing. We are now presenting an automated pipeline for identifying and extracting only the skeleton load-bearing structure from the dense point clouds to generate clean simulation-ready FEMs, and we call it Scan2Beams as a first approach. Because the proposed workflow from the whole project is we have three main pipelines, let's call it like that. The first I'm going to present today is the Scan2Beams, where it's about getting the point clouds of the building, then have the structural element recognition, and develop an algorithm for this automated structural geometry and analytical model generation. However, in future, we also need to look about the hinges, about the joints. So we will go through the building and capture with the photogrammetry and pictures the knots, the hinges, and the supports, and create a deep neural network who automatically classifies the hinges, the degree of freedom, and so on, and imports that into the analytical model to have this automated joint recognition. And furthermore, of course, we also need to look at the material information. So how we conducted our research methodology-wise. So this Scan2Beams development, it's a development in a Python code, and as I said, for automatic classification and dimensioning, and integrating the material and cross-section data from plans manually. The output is a FEM Reddit model. So for data acquisition, we went through 7, now 8 industrial building structure. They're mostly reinforced concrete and hybrid steel concrete skeleton structures. And we've put a GoPro 360 on a drone setup and optimized flight paths for full spatial coverage. So we flew through the buildings. was also very relevant for the frameworks to really get into look from each side. Yeah, and in this study we conducted a proof of concept of the developed Scan2Beams algorithm on a precast concrete hall in Austria, and we do a manual validation against floor plans and about the geometric accuracy and classification precision. So how does this Scan2Beams pipeline look like, or what are the key processing steps? First, we have the point cloud processing and discretization. So we're given a 3D point cloud input, which is a collection of 3D coordinates representing the structure. The data is discretized into a structured grid with a user-defined resolution. And within each grid cell, the points are accumulated into cells, which allows us the evaluation of the point density, the spatial distribution, and the structural relevance. The discretization also provides us an organized framework to track the point memberships and the structural relevance across the scans. And then we have this heuristic pre-filtering, searching for vertically and horizontally aligned point clusters with the assumption that columns and beams are always axis aligned and span full structural dimensions. And the structural element extraction, there we incorporate a process which leverages the geometric information about the configuration of the industrial skeleton. And yeah, and afterwards we do some post-processing with hue transform line detection applied on an X, Y, XZ and YZ plane of this discretized grid, and to identify the linear geometry of the structural beams and the columns. And these detected lines are then subjected to refinement processes which involve filtering, and the filtering is based on orientation, length, density, and spatial alignment. And finally, once we've identified the structural axis for columns and beams, we export it to a finite element model, which is the structural reconstruction in an FEM model. However, for that study at the beginning, we used global RFM. This is the captured use case. It's an industrial building in Lower Austria, which was constructed in 1980 and has undergone some important renovations. So the structure is a 2-aisle hall with prefabricated reinforced concrete skeleton. We have concrete columns with forked supports and 40 times 40 centimeters course section and a room height of 6 meters. Yeah, the T-beams are single span precast concrete T-beams with a 6 meters length and 80 centimeters height. And the building is covered with walls and roofs out of aerated concrete walls and trapezoid sheet metal facade. So here you see the proof of concept. So we got the point cloud, so the 3D scan of the industrial hall in point number 1. Which is, yeah, and then it detects the line, it projects the points on planes and aggregates them into the grid size cells. Then the third point is the strong lines. It filters them on the threshold, defining the line endpoints. And finally, it identifies the extracted structure in point 4. It clusters the lines into beams, removing the single line clusters. And finally, it identifies the beams and the joints where they intersect, and the segmenting beams, yeah, are modeled according to the joint connectivity. And finally, we received the computable finite element model. As you see, we just did it on a smaller application case, not for the whole building, but this is often the advantage of industrial buildings. They're very regular. And what I also didn't mention, we also have incorporated damage detection. So actually we also have the data in our point clouds where there is already some damages in the concrete structure, but this is, we will show in future papers. So yeah, so we were able to do the manual validation, which aligns which confirms the alignment of the extracted geometry with the structural layout. We did it by plan documentation. And we effectively identified the axis-aligned beams and columns in a real industrial use case. And so the initial results now indicate robustness in extracting relevant structural skeletons. However, there are limitations, of course, so we didn't do any quantitative metrics yet due to the missing reference data to do a full statistical evaluation. And our ongoing work aims to benchmark the accuracy, the precision, the recall, and the geometric deviation. Furthermore, so we will do a planned validation across diverse building types, across diverse scanning conditions, and of course also the Scan2Beams algorithm also has to be tested then on the steel structures. I will go a little bit faster here. So the future outlook, as I already presented before, there is still now manual parameter input necessary from the user. So in future we will also create some models which read from existing documentation and enrich our finite element models automatically. Furthermore, we will have this joint behavior and cross-sectional properties extraction. So we apply a learning-based method for this joint type classification and automated modeling for the degrees of freedom. And yeah, and hopefully we can broaden the application to diverse industrial typologies in future. Thank you.